Hey everyone! So in this video I'd like to introduce the tangent function as well as the reciprocal trigonometric functions. So we've already introduced two functions, two trig functions, the sine function and the cosine function, and these two functions are going to be the most important of all of the trigonometric functions we'll learn in this class. But here there are going to be four more that will appear regularly throughout this class, and I'd like to introduce them in this video. And so here let's start by reminding ourselves what the sine function and the cosine function mean. So if I have a circle of radius r and an angle of theta, so let's draw this angle here, I'll label it theta. Well, this angle is going to cross this circle at a point, and I'm going to label that point by its coordinates, so its x coordinate and its y coordinate. And so we said that the sine function, well, it's going to take this angle of theta in as an input, and it's going to return the ratio of the y-coordinate, so this distance here, divided by the radius of the circle, so y over r. And then the cosine function, well, it's again going to take in this angle as an input, and what it gives back is this distance x divided by the radius of this circle. And this ratio, it stays the same regardless of the radius of the circle, and so although we've defined sine and cosine this way, usually we'll view sine and cosine in terms of the unit circle where r is equal to 1. And so one more ratio I'd like to bring up is this ratio that we'll call tangent. Comes from this tangent function, so tangent of theta. So that's a new function. It'll take in this angle and it'll give back the ratio of y divided by x. So this is another trigonometric function that we'll use quite regularly throughout this class. And although we've defined it this way as y, or the y-coordinate divided by the x-coordinate, this is actually not the way we'll usually see this tangent function appear in our class. And so here, maybe let me show you the way we'll usually see this function appear. So usually we'll see tangent as the ratio of sine of theta divided by cosine of theta. And let me show you that really this ratio here, sine of theta divided by cosine of theta, is really the same as y over x, that ratio I've written above for our tangent function. And so here, we've defined sine of theta as the ratio y over r. And cosine of theta, well, it's the ratio x over r. And so here we've got this fraction within fractions. And this is really just telling us to divide these two fractions. And so let me just rewrite it that way. Maybe it'll come out a little more clearly. If I have this y over r in the numerator and x over r in the denominator, that's really the same as y over r divided by x over r. And so how do we divide two fractions? Well, we multiply by the reciprocal of the second fraction. So here I can rewrite this as y over r multiplied with r over x. And so when we multiply these two fractions, we multiply their numerators together, then we multiply their denominators together. And we see a common factor of r in the numerator and the denominator. So these factors of r would cancel out, and we'd just be left with this ratio, y over x, like we defined a moment ago, or like we saw a moment ago, as the ratio of our tangent of theta function. So all this to say that usually when we describe tangent of theta, we're going to be thinking of it in terms of this ratio sine of theta over cosine of theta. But I just wanted to define it the way we defined our sine and cosine function first. And so before we really dig into using this tangent function, let me just go ahead and define the remaining trigonometric functions that we'll talk about in this class. And usually we'll refer to them as the reciprocal trigonometric functions because they come from taking the reciprocal of the previous three trigonometric functions, the sine, cosine, and tangent function. And so the first one I'd like to introduce is referred to as cosecant. So here, cosecant, usually we'll label it with CSC. This is the trigonometric function that's the reciprocal of the sine function. And so the reciprocal of the sine function, I can write that as 1 over sine of theta. And maybe just to make this very explicit, right, we said that sine of theta was y over r. Well, the reciprocal of y over r is r over y. And so, usually when we think about this cosecant function, we'll think about it as 1 over sine of theta, but in case you want it in terms of the coordinates and the radius of the circle, you can also think about it as r over y. And then the secant function, well, this is the reciprocal of our cosine function. So this is abbreviated as SEC, secant of theta. And so this is 1 over cosine of theta. And in a similar way, we can write this as r over x, the reciprocal of our cosine function. But again, usually the way you'll want to think about the secant function is just as 1 over cosine of theta. And then the last of the remaining trigonometric functions that I'd like to introduce is the cotangent function. And so here we usually abbreviate it as COT. This is cotangent of theta, and this is 1 over tangent of theta. And we define tangent of theta as sine of theta over cosine of theta. And so the reciprocal of sine of theta over cosine of theta, well, that's going to be cosine of theta over sine of theta. And earlier we said that tangent of theta, well, that's the same as y over x. So the reciprocal of that you can view as x over y. So these are many different ways to think about the same function, cotangent, but the way we'll usually think about it is just in terms of sine and cosine. Really, all of these reciprocal functions you can think of just in terms of sine and cosine, and usually that's sort of the simplest way to deal with them. Okay, so we've defined 3 reciprocal trigonometric functions now. But how do we go about remembering which trigonometric function is the reciprocal of which? Well, hopefully it's pretty memorable that the cotangent function is the reciprocal of the tangent function. Now, the way I remember that cosecant is the reciprocal of the sine function and secant is the reciprocal of the cosine function is that really I see them as sort of the opposite of what I'd expect to match. Right? I'd kind of expect the cosine function to match with the cosecant function. They both share that prefix co, but that's not the case. Those aren't the ones that match up. And so that's the way I remember that cosecant matches up with sine, and secant, well, that matches up with cosine, so the reciprocal of the cosine function. Okay, so let's evaluate these trigonometric functions at different angles. And let's start with tangent of pi over 3. And so one thing I like to say before we really begin evaluating these expressions is that, here at tangent of pi over 3, tangent is a function, and that pi over 3 is there as the input to that function. And usually when we're dealing with functions and inputs, the input is usually wrapped around in parentheses. But sometimes with trigonometric functions, the parentheses aren't included. And so even when we don't see those parentheses there, beside that trig function, we need to be able to interpret that pi over 3 as the input of that trigonometric function. Whenever there's ambiguity, maybe that's when you really want to include parentheses, but sometimes you won't see the parentheses and you still need to interpret that number beside that tangent function as the input. So it's not multiplication. I can't do anything like multiplication, like factoring out. I can't move that pi over 3 around anywhere. If there's something dividing that tangent of pi over 3, it won't be able to interact with that pi over 3. Really, that pi over 3 is there just to be seen as the input to our tangent function. And so how do we evaluate tangent of pi over 3? Well, the way we usually do this is we see this as sine of that same input, sine of pi over 3, divided by cosine of that same input, cosine of pi over 3. And so now we just need to evaluate sine and cosine of pi over 3. And to do that, we draw pi over 3 on our unit circle. And so this is pi over 3. This is our 60-degree angle. And here on the unit circle, well, the bottom leg length of that triangle, that right triangle, that special right triangle, is 1/2. It's a short side length of that 30, 60, 90 triangle. And the long side length, the long leg length, is the square root of 3 over 2. And so sine of pi over 3, well, it's that long leg length. It's that y-coordinate of that point, which we can see as a long leg length. That's the square root of 3 over 2. And then cosine is that short leg length. It's that horizontal coordinate of that point on the unit circle there. And it's 1/2. And so we can divide these fractions by multiplying by the reciprocal. Another way we can sort of clear up this fraction is we can multiply by 2 over 2. Right? So any fraction, we can multiply the same number to the top and the bottom, and we'll get an equivalent fraction. And so the square root of 3 over 2 multiplied by 2, well, that's just the square root of 3. And then 1/2 multiplied by 2, well, that's just 1. And so I could write this out as just the square root of 3. Right, so tangent of pi over 3 is just the square root of 3. Okay, so what about cosecant of 7 pi over 6? How do we compute this function? Well, this is the reciprocal of which trigonometric function? It's the reciprocal of the sine function. So this can be computed by evaluating 1 over sine of 7 pi over 6. And so now what's sine of 7 pi over 6? Well, 7 pi over 6, this is pi over 6 past pi. So we can also see this as 30 degrees past 180 degrees. And so here I can imagine drawing this 30, 60, 90 triangle here. So here this is 7 pi over 6. And so here we've got this 30-degree angle here, this 60-degree angle here. And so this is a side length of 1/2, side length of the square root of 3 over 2, side length of 1 if we're looking at a unit circle. And so here, sine of 7 pi over 6 is going to be the y-coordinate of this point on the unit circle. And because that side length of that triangle is in the vertical direction is 1/2, well, sine of 7 pi over 6 is going to be negative 1/2 because it's below the x-axis. So this is 1 over negative 1/2. And so if sine of 7 pi over 6 is negative 1/2, well, the reciprocal of this is just going to be negative 2. And you know, we can do this by taking 1 divided by negative 1/2. And that would amount to multiplying by the reciprocal of negative 1/2, which is negative 2. So 1 multiplied by negative 2, that's just negative 2. Okay, so for this last example, secant of 7 pi over 4, to compute this, we can view this as the reciprocal of our cosine function. And so this is 1 over cosine of 7 pi over 4. And so to evaluate cosine of 7 pi over 4, we need to find out where 7 pi over 4 is on this circle. Well, 7 pi over 4, that's pi over 4 shy of the full 2 pi rotation. And since pi over 4 is 45 degrees, we're 45 degrees away from the full rotation of the circle. And we're dealing with this 45, 45, 90 triangle, where the side lengths are the square root of 2 over 2, the square root of 2 over 2, with a hypotenuse of 1. And so here, this angle here, this is 7 pi over 4. And so we'll have 1 divided by cosine of 7 pi over 4 is the x-coordinate of this point on the unit circle. So this is the square root of 2 over 2, and then dividing 1 by the square root of 2 over 2, that's the same as multiplying by the reciprocal of the square root of 2 over 2 to 1. So here we have 1 divided by the square root of 2 over 2, which amounts to multiplying by the reciprocal of the square root of 2 over 2. This is 2 over the square root of 2. And here sometimes people like you to rationalize the denominator, but that's okay, we don't have to in this case. I'm not too picky about that. This is fine for us. So here I've got 3 more examples of these reciprocal trig functions and tangent that I'd like you to compute. So take a moment, pause the video, see if you can evaluate these different examples here. So secant of 3 pi over 2, this is 1 over cosine of 3 pi over 2, right? Secant is a reciprocal to our cosine function. And so 3 pi over 2, well, that's 3 sets of pi over 2, or 3 sets of 90 degrees. So that ends up here on our unit circle. And so cosine, the x-coordinate of this point on the unit circle, well, that's 0, right? This point here is point 0, comma, -1. And cosine is that x-coordinate on this point on the unit circle. And so we end up with 1 over 0. And 1 over 0, this is undefined. What about cosecant of negative pi over 3? Well, negative pi over 3, that's a clockwise rotation around our unit circle of pi over 3, so 60 degrees be roughly here. And so if this is a 30, 60, 90 triangle, the short side length, that's 1/2. And the long side length, that's the square root of 3 over 2 in the negative direction. And so cosecant is the reciprocal of our sine function. So we're looking at sine of negative pi over 3. And here, sine of negative pi over 3, well, it's coming from this side length here, square root of 3 over 2, but in the negative direction. So this is 1 over negative square root of 3 over 2. And so taking the reciprocal of that negative square root of 3 over 2, that's negative 2 over the square root of 3. And then in this last example, tangent of 3 pi over 4. And so tangent we can compute as sine of 3 pi over 4 divided by cosine of 3 pi over 4. And this is equal to, well, here let's draw 3 pi over 4 on the unit circle. So that's 3 sets of 45 degrees, right? 3 sets of pi over 4. And so we've got a 45, 45, 90 triangle here between this angle and the x-axis. And so again, we've got this negative square root of 2 over 2. We've got square root of 2 over 2, side length of 1. And so here, right, sine of 3 pi over 4, well, that's above the x-axis, so it's positive. This is going to be the square root of 2 over 2. We've got cosine is going to be the, well, square root of 2 over 2. This x-coordinate is in the negative direction, so here we've got negative square root of 2 over 2. And so a number divided by its negative is just going to be -1. So before I wrap up this video, I'd like to talk about an intuitive way we can think of the tangent function. That'll be pretty useful in this class. And really, maybe I'll just say it outright. So this tangent function, tangent of theta, one way it can be interpreted is as the slope of the angle theta. So tangent of theta can be seen as the slope of the angle theta. And so for example, if I draw out some angle theta, it's going to meet with this circle at some point. Maybe I'll label this point x, comma, y. And so here, how do I find the slope of this angle theta? Well, I take 2 points and I take the ratio of the change in y divided by the change in x. So here, another point I see on this this line going through this angle is the point 0, comma 0. And I could find the slope by taking, the difference in the y value, so y minus 0, and dividing by the difference in the x values, so x minus 0, and we get y over x. Right? So here the change in y is just that y value there, and the change in x is just x if we're going from 0 to x and 0 to y. And so here, we said earlier that tangent, we can see this as sine of theta divided by cosine of theta, but earlier we also defined it as y over x. And so really this slope here of our angle of theta, that's really the same as tangent of theta. And so this is helpful because it gives us a way of sort of evaluating or having some idea of the size of tangent rather quickly. For example, I can ask you the question, what is larger? Tangent of 7 pi over 6 or tangent of 4 pi over 3? And we don't even have to compute these to know which one's larger, right? Maybe I'll just draw these above in our unit circle. One angle here is 7 pi over 6, that's pi over 6 past pi, so 30 degrees past 180 degrees, so this is 7 pi over 6. And then I can also draw out 4 pi over 3, so 4 pi over 3, that's pi over 3 past pi, so 100 past 180 degrees, it's 60 degrees past 180 degrees, this is 4 pi over 3. And if tangent is the slope of our angle, well, which one has the larger slope? Which one has a steeper angle? Well, it's this 4 pi over 3, right? Without even computing tangent of 4 pi over 3, I know right away that it's a larger value than tangent of 7 pi over 6. So this is not the only useful thing we can draw from knowing or recognizing tangent as the slope of our angle theta. Here maybe I'll sketch out one more example. So let's say I've got some angle theta here. Maybe another question I can ask is, what's another angle that tangent will give me the same value for? So maybe I'll say, what other angle produces the same value as tangent of theta, where theta is the angle in our picture? Well, of course, if we go all the way around the unit circle, a full 2 pi on top of theta, we'll get the same tangent value because we're going to end up at the same point here and get the same ratio y over x of the same y value and the same x value. But here, if tangent is the slope of our angle theta, and I kind of imagine this line going through this angle theta, where do we get the same slope? What other angle would give us the same slope? Well, if we were all the way on the other side of this unit circle, we would be on the same line. This angle would fall on the same line and it would have the same slope. Well, what's the angle on the other side of the unit circle? Well, it's 180 degrees added onto this angle. And if we're talking about radians, well, it's pi added onto this angle, so theta plus pi. This is also going to give us the same slope because this angle ends up on the same line, and so it'll give us the same value of tangent. So here, really the point or the punchline is that tangent of theta is going to be the same as tangent of theta plus pi. And what we're really saying here in this description is that the period of tangent is pi. And what I mean by that is that tangent repeats itself every pi radians, whereas sine and cosine, they'll repeat themselves only when we go all the way around the unit circle. They'll repeat themselves every 2 pi. Tangent is going to repeat itself every pi.